Okay, we're going to talk about 12.2 today. I am going to start with some warm-up questions here because we're going to do a little bit with Venn diagrams. So going over those. So the results of a survey of car owners are shown in the Venn diagram. How many people own a van and a sedan? So you find van, which is the green, and sedan, which is the blue. A lot of people like to say 6, but the answer here would be these together, which would be 11. Own only a sports car, so nothing else. You're going to look for the purple circle, but nothing crossing over, and that's going to be the 24 that are here. So just to be clear, the 24 that is here is not all of this put together. The 24 that's here is what is outside of this part of the Venn diagram there. Okay. Own only a van. So only a van would be the 15. Same idea there. Own a van, a sedan, and a sports car. So all of those things would be the crossover, the 5 that are there. And how many people were surveyed? So you're going to add all of it together. So you're going to have the 15. Let's see, there's 20, there's 27, 29, 30, 65, and 24. Let's see if I can add all these together. So we're going to have 89 that were surveyed in that case. Let's check and make sure I did all that right. Yep. So that's what we would have there. So just a quick reminder of Venn diagrams. Okay, so we're talking Venn diagrams here. We're going to talk about the terms intersections and unions. So when two events, A and B, occur, the intersection of A and B is the set of all outcomes in the sample space of event A that are also in the sample space of event B. Okay, in the Venn diagram, the shaded portion represents the intersection. So this is the intersection right here. So we've got the word intersection. We've got the symbol for intersection, which is this upside down U. To determine the probability of an outcome from the intersection of two or more events, find the ratio of the number of outcomes in both events to the total number of possible outcomes. Okay, so the number that would end up in this intersection out of the total possible outcomes that are there. And so that's shown here, and you can see that. But hopefully that makes sense as you just figure out how many fit in that event and out of everything that's there. When two events are in a union, yeah. Okay. And then this is with the word and. There you go. That's what I was missing. Okay. So when two events occur, A and B occur, the union of A and B is a set of all outcomes in the sample space of event A with event B. So a union is actually going to be a right side up U, just like a U that's a union that's there or whatever. And it's going to be, if I were to look at this Venn diagram again, it's all of the green and all of the blue put together, not counting the overlap twice, only counting it once. So the union is, usually we use the word or. It's in this or that, which includes the overlap of it. Okay. So the probability of that can be found lots of different ways, or the number of events in it can be found lots of different ways. You can count the different groupings like we did in our Venn diagram earlier, or you can find the number in A, the number in B, and subtract the number that's in both. Because if you find the number of events in this circle A, and then you find the number of events in this circle B, you have now counted the ones that are in this little space twice. So that's why they subtract the intersection once there. Okay. So you can either find the ones that are only in A, the ones that are only in B, and the ones that are in the intersection, add those together, or you can find all of A, all of B, and subtract the intersection once. Okay, so that's what you're seeing here. So that's the idea of how to do that. Okay, so we talked about the intersection symbol. So we have that as the probability of A and B, okay? And then the union symbol, the probability of A or B, okay? So we have those numbers and what they're associated with. Okay, so check here. So let's do a spinner problem. Let A be the event of the spinner landing on a blue section. Okay, so A is a blue section, and B be the event of this spinner landing on a section with a number divisible by 3. We're going to do a little bit of math here. Okay, what are the possible outcomes of each event? So A, 7 would be a blue section, and 15 would be a blue section. So those would be the outcomes. You either got 7 or you got 15. Okay, B, number divisible by 3. So 3 is divisible by 3, not 5, not 7. 9 is divisible by 3, so we should add that to it. And 15. Those are all of the numbers that are divisible by 3. So A intersect with B. Which ones are in the intersection of it? We circled for both is the number 15. So 15 would be in the intersection. Now, sometimes the intersection is the empty set, so just remember that as well. Okay, then that leads to complements. So if we go back to our A and B Venn diagram that we have here, we can talk about the complement. So the complement of A consists of all the outcomes in the sample space that are not included as outcomes of event A. Okay, so a complement of event A can be noted as A prime, as shown in the Venn diagram. So A prime, if we said we had like one outcome that wasn't in A or B, we had 2 here, we had 3 here, we had 4 here. So if I give you all of those numbers, A prime includes everything not in A. So you take all of A and you get rid of it and you count everything else. So you would count the 1 and the 4 that are here, and there would be 4 possibilities in there. Okay, so not included. The complement of A can be noted. Oh, sorry, I did that one already. The probability of rolling a die and getting a 3 is 1/6. What's the probability of not getting a 3? So everything other than that, there's 5 possible outcomes. So that would be 5 out of 6. Okay, or you can also do it as 1 minus the probability of getting the A that's in there. So that's what you're seeing as that complement and the probability of a complement. And we'll work through some of those too. Okay, so our last example here is we have a raffle. So in this raffle, the Harvest Fair sold 967 raffle tickets for a chance to win a new TV. Complete the table to find each probability of not winning the TV with the given number of raffle tickets. So if you got 20 raffle tickets, okay, then you're going to do 967 minus 20. So you're going to find 947 out of 967. So probability of not winning here would be a 98% chance. Okay, now you can do it that way, or you could do it as 1 minus, and then you could do 20 out of the 967. So you can do either one of those. And it's 1 because 1 represents 100%, just to clarify that. And then the 20 out of 967 would be the percent chance of you winning. So you had a 98% chance of not winning in that case. If you buy 200 raffle tickets, then you would either do 767, so I just subtracted 200 from this, out of 967, or you would do 1 minus 200 out of 967. And again, it doesn't matter which one you do. And you would get a 79% chance of not winning. So still not great, even though you bought 200 raffle tickets. If you bought 100 raffle tickets, you would do 867 out of 967. Or you could do 1 minus 100 out of 967. Hopefully you get that idea. This would give you an answer of 90%. Okay, you got to move your decimal too. Don't forget that. If you only bought one measly raffle ticket, you can either do 966 out of 967, which you can imagine what that's going to come out to, or you can do 1 minus 1 out of 967. These both come out to the same thing, and it comes out to the closest that we can get is you have a 99.9% chance of not winning. Okay, so you decide if you want to buy a raffle ticket or not based on that, but that's what the information you have.